This video is for Math 70, and this assignment is kind of a bridge between the topic that we were just finishing up on graphing and the topic that we're moving into on solving systems of equations. And this first assignment is about solving systems of equations by graphing. And this is a very common thing that people do mathematically in the sciences. We frequently have a system of equations involving the same variables, and if you've got information about those variables, you can generate some solutions that will be helpful to you. So, and we'll see some examples of this in terms of word problems. Now, when we get to the word problems, you may say to yourself, well, these are actually not real life problems. Well, for one thing, many of those problems are actually real life problems. But at the same time, even the ones that are kind of cookie cutter problems, they really reflect very real situations that scientists and mathematicians and anyone really who works in a discipline where you can have equations. These are things that people run into all the time, and I think that those word problems are really a reflection of that. So we'll put that off to when we get to the word problems. For right now, let's talk about solving systems of equations and how to do that through graphing. So first off, let's just talk about what a system of equations is and what a solution to it might look like. So in problem 2, I've got these two equations, and I'm asking, are any of these points a solution to both equations? Okay? So when I talk about the system, we're talking about both equations at once. So determine if any of the ordered pairs is a solution to the given system of linear equations. So the idea here is that, let's plug them in and find out. If x is 0 and y is 2, does that equal 2? Yes, so I'm just plugging it into the first one. All right, how about the second one? If x is 0 and y is 2, does that equal 4? No. So this one's not a solution. Okay, so that's ordered pair A. Ordered pair B is -1, -2. So if we do -1 minus 2, is that equal to 2? No. We don't even need to check the second one. I mean, I can check it if we really want to, but as long as if it doesn't satisfy one of the equations, then it doesn't satisfy the system. All right, what about 3, -1? So 3 plus -1, is that equal to 2? Yes, good. All right. Let's see here. There we go. What about the next one? Is 3 minus -1 equal to 4? Yes, it is. Okay, so that says that ordered pair C satisfies that system of equations because it satisfies both equations. All right. Let's look at one more of these, and then we'll move on to the systems where we want to solve them by graphing. Problem 4, 2x minus y equals -3, and y equals 2x plus 3, and our ordered pairs are 2, -1, 0, 3, and -1, +1. Okay, so again, let's just plug them in. So for A, let's see, we're going to have 2 times 2 minus -1. Is that equal to -3? Well, this is 4 plus 1, so no, it's not equal to -3. And again, like I said, if it doesn't satisfy the first equation, we don't have to plug it into the second one, because it has to satisfy both. All right, let's see. If x is 0 and y is 3, does that equal -3? Yes. Check. What about the second one? If y is 3 and x is 0, does that satisfy the second equation as well? I'm hesitating here because I'm realizing this is actually the same equation twice. 2x minus y equals negative 3 and y equals 2x plus 3. This is the same equation, right? If you add your y over here, add the 3 over here. So it's not really a system of equations in number 4. But in any event, if we pretend that it is, yes, the point 03 satisfies both of those equations. All right, what about the next one? 2 times negative 1 minus 1, is that negative 3? Negative 2 minus 1 equals negative 3? Yes, that one works. And the next one will work because it's the same as the first one. I'll plug them in, but let's see here. So 1, is that equal to negative 2 plus 3? Yes. So both of these points work. All right. Now let's look at an actual system and talk about how to solve it by graphing. So, problem 6. We get the system x plus y equals 2, x minus y equals 4. So, you don't have to put these in slope-intercept form, but I always find it much easier to graph something if it's in slope-intercept form. So I'm going to take this first equation, move the x to the other side, take the second equation. Let's see, I'm going to add y to both sides and subtract the 4 over, and that gives me y equals x minus 4. So here's our two equations that we need to graph. So the first one, we've got a y-intercept of positive 2 and a slope of negative 1. So that's y equals negative x plus 2. And then this one, y equals x minus 4. So we go down to the point 0, negative 4, and this one has a slope of 1. And that's our solution. That's the point that satisfies both of those equations. Now, because I'm sketching these graphs, it's kind of hard to tell what that point is, and so I took the time to put these graphs on paper so you can see what they look like on the grid. And that's really the key to generating these solutions, is to have this on the grid so you can see what your solution is. And so, let's see here. So there's the paper version of this. You can see there's the two lines, and then I've identified that intersection point, 3, negative 1. Okay? So let's see, let's get the focus back on the board. There we go. And now I can identify this point appropriately as 3, negative 1. And we can check our answers too, right? If x is 3, y is negative 1, does that equal 2? Yes. Let's see, if x is 3 and y is negative 1, does that equal 4? Yes, it does. Okay, so there's our solution. So that's the idea with these. We want to graph them on a grid and then find the point of intersection, and that will be the solution to this system. All right, so let's work through a few more of these. I've got paper graphs for them so that you can see the intersection point and what the coordinates of that intersection point are. Let's see, let's go and do number 10. Something I was thinking about yesterday is, if you're watching these videos and it's helpful to you, then that's great. If you find yourself struggling to understand what's happening, I would recommend that you stop the video and then do an odd problem. Like when I do problem 6, you might stop the video and go back and do problem 5 and see if you can do that one correctly. But I do recommend, stopping and thinking about the process rather than sitting and listening, although taking notes is very helpful as well. All right, let's look at problem 10 here. X plus y equals 6. negative x plus y equals negative 2. Okay, so again, if we're going to graph these, then I'm going to put them into slope-intercept form. So we get y equals negative x plus 6. And then the second one, I'll add x to both sides. And this will be y equals x minus 2. All right. So let's see here. If I go up to positive 6, and then this has a slope of negative 1. So we go up 1, back 1, up 1, back 1, and so on. And that's y equals negative x plus 6. The other one, x minus 2, will start here. And there's our intersection point right there. This is y equals x minus 2. And again, because I'm not doing this on a grid, it's a little bit difficult to tell what that point is. So let's look at the paper version here. Let's see here. There we go. That's a pretty good look at it. There's the two lines I've graphed, just like I did on the board, except with the grid you can see that the intersection point is the point 4, 2. Okay, so let's identify that on the board as the point 4, 2. And then you don't have to check your answer, but it is, I think, nice to know whether or not these are actually true. All right, 4 plus 2 equals 6, good. Negative x plus y is negative 2. Negative 4 plus 2 is, is that negative 2? Yes, it is. Okay, so that is helpful. Let's take a look at problem 12. So, problem 12. 5x minus 2y equals 10. X minus y equals negative 1. Okay, so when I see this negative y, this is when I like to move the y to the other side and leave the x where it is. And it doesn't matter. I'll do it a different way in just one sec to demonstrate that it's not important how you go about doing this. Let's see. Now we want to subtract the 10 and move it back over with the x. So we get 5x minus 10 equals 2. And then we've got to divide everything by 2. Okay? That's something that's tricky. People are used to just dividing in 2 places. But if you multiply or divide on both sides, you've got to multiply everything or divide everything. And that's really important. So 5 over 2x minus 5 equals y. So there's one line. I talked about doing this a different way. So let's talk about that. 5x minus 2y equals 10. So if I move the x over, there's nothing wrong with that, but don't lose that minus sign in front of the 2y. Okay? And now we've got to divide everything through by the negative 2. So here we get y. This will be positive 5 over 2x and negative 5. So we get exactly the same thing. I find that this just has more room to make errors, but again, whatever makes the most sense to you, I think is the way that you should go about doing the problem. That's one of the beautiful things I think about is true of mathematics, is that you have choices. Okay? All right, so x minus y equals negative 1, so I'll add the y over, and then add the 1 to put it with the x. So there's our two lines. Y equals x plus 1 and y equals 5 halves x minus 5. I'll draw a sketch over here. let's see, x plus 1 is just going to look like that. And then 5 halves x minus 5. Let's see, 1, 2, 3, 4, 5. And then 5 halves will take us up 5 and over 2, and up 5 and over 2. And so it'll look something like this. So there's our intersection point. Like I said, it's kind of hard to tell exactly where that is. So let's take a look at it on the grid. So there's the paper version. There's the two lines, and you can see that intersection point is the point where x is 4 and y is 5. Now let's get this to focus. There we go. Okay, so this is the point 4, 5, and that should be the solution to our system of equations. Okay, let's keep moving on these. We'll look at a couple more. Okay, let's see here. Problem 14. What do we have? 4x minus 2y equals 8. 2x plus y is negative 4. Okay, well, in the first one, 4x minus 2y equals 8. I'm going to add the 2y to both sides, and then subtract the 8 to go over with the x. 4x minus 8 is 2y, and then we've got to divide everything through by 2. So y is equal to 2x minus 4. So there's one of the lines that we're working with. This one over here, we can just subtract 2x on both sides and say y equals negative 2x minus 4. Now, if you look at these equations, you might be saying to yourself, well, it looks like they have the same y-intercept at negative 4. And that is true, okay? One of them's got a slope of positive 2, which will do something like this. The other one's got a slope of negative 2, which looks something like that. And this one, I don't really need the grid to tell what the solution is, because the solution is the y-intercept, 0, negative 4. Okay? And you can see if x is 0, then y being negative 4 would make this true. And if x is 0, then there you go, y equals negative 4. So that's relatively straightforward. Okay, well, let's look at another one here. Okay, let's see here. Problem 16, 5x minus y equals 10, 2x plus y equals 4. All right, so again, let's see. 5x minus y equals 10. Well, I'll do this by moving the x over. Subtract 5x on both sides. Don't lose that negative sign, because that's a minus y. And then, to get this into slope-intercept form, we've got to get it to be positive y. And so positive y will be equal to positive 5x minus 10. So there's one line. The other line is going to be, if we just subtract 2x on both sides, y equals negative 2x plus 4. All right, let's see what the sketch looks like. So there's the y-intercept for this one at 0, 4. A slope of -2 will look something like that. 5x minus 10. So there's 0, -10 for the y-intercept. And then a slope of 5, I think is going to do something like this. And if I remember correctly, that is the intersection point there on the x-axis. But let's take a look at the paper version before I conclusively say that. Yeah, so there's the graph, and you can see that point of intersection is where x is 2 and y is 0. All right. So that solution there is the point x equals 2, y equals 0. Okay, well, let's look at two more. Okay, problem 18. Let's see, 2x minus 4y equals 8, and 2x minus y equals -1. All right, let's see. First one here, 2x minus 4y equals 8. So I'll add the 4y over and subtract the 8. And then we've got to divide everything through by 4. Okay? So y equals a half x minus 2. So there's one line. Let's see the other one. I'm going to add the y over and then add 1 to put it back with the x. So there's the second line. Okay? So 2x plus 1, there's our y-intercept at 0, 1, and a slope of 2 is going to look something like that. A half x minus 2, so there's our y-intercept at -2, and a slope of a half is going to go something like this. So y equals a half x minus 2, and y equals 2x plus 1. So let's take a look at the paper version and see where on the grid that solution actually falls. And so there it is, and there's the solution where x is -2 and y is -3. Okay. There's our solution, -2, -3. Okay, let's look at one more here, problem 20. Problem 20, these equations are in slope-intercept form. Y equals 3x minus 4, and y equals -2x plus 1. So these are all ready to be graphed. Don't really have to do too much work to get started. So this one right here, -2x, there's the y-intercept at +1, the point 0, 1. A slope of 2 will be something along those lines. 3x minus 4, so our y-intercept is down here at 0, -4. And the slope of 3 is going to be something like that. I guess that could be the point where x is positive 1 and y is negative 1, but I think it's better to look at the grid before we draw any conclusions. And there it is on the grid. Yeah, where x is positive 1 and y is negative 1. Now, if we knew that this solution had to be whole numbers, then I could guess that that was going to be where x is positive 1 and y is negative 1. And if you'll notice, all of these solutions, I mean, if you look at the answer key, all of these solutions are whole number solutions. Not every system of equations has whole number solutions, okay? It's just that if you're graphing on a grid, it's very, very helpful to have those solutions fall on the whole numbers. So that's the way I've set all of these problems up, okay? When we move on, so there are 3 different methods for solving systems of equations. This is the first one we're talking about, which is solution by graphing. Then we'll look at solution by, well, I'm not sure which order we're going to go in, but we're going to look at solution by substitution and solution by adding or subtracting the equations together. So I'll say that, and then we'll look at word problems for an application of this idea. Okay, so those are the next 3 assignments really that are coming down the road. This solution by graphing, like I said, on the grid, it's helpful to have whole number solutions. As you get into more and more sophisticated mathematics, you will find these solutions using technology, and they are frequently not whole numbers. Okay? But as with anything, when we're just getting started, I think it's helpful to simplify these ideas so that we get a sense of what's happening, and then as we move forward, you'll see more complicated and challenging examples of these ideas. Okay, so that's it for this assignment. As always, if you have any questions, please let me know. Thanks.